Let's continue on sliding window flow control. We got through some basic parts of it last week, but we need to get through and see how it operates in full. And then see how it compares to stop and wait by going through an example and some calculations. And one of the handouts that you have, or I'll give you in a moment, gives you a better picture of sliding window flow control. So just recapping on what we know about sliding window, the aim is to allow the source to send multiple frames before having to wait for an ACK. Because one of the problems with stop and wait is that we send one frame, then we spend time doing nothing, waiting for an acknowledgement coming back. Therefore our throughput or efficiency goes down. If we can send multiple frames and then wait for an ACK, we can have higher throughput. We use sequence numbers. Every frame that we send has a sequence number, and those sequence numbers wrap around. If we have a 4-bit sequence number, with 4 bits we can go from 0 up to 15. And then we go back to 0 again and keep going depending on how many frames we have to send. So if we're transferring a large file, or in fact we have a connection that runs over hours or days, we may be transmitting thousands, millions of frames. We just keep wrapping around the sequence number. The sender and also the receiver keep track of some state of the set of frames that they're allowed to transmit. Have you got your handouts? Have you got a handout? Yes. Good. If you haven't got the handout for today, I'll give them out in a moment. Let's first get up to how the basics of sliding window flow control works. The sender keeps track of 3 things. The set of frames that have been sent and have already been acknowledged. Think of these frames as completed. Sender has sent the frames, received an ACK for them, successful, it can forget about those frames. In the diagram, it's these frames to the left of this vertical bar. Of course, the sender in software doesn't have this graphical picture, it just keeps a number of variables, like the number of the frame or the last frame acknowledged, number 5. And because the numbers of frames go in order, sequence numbers, if frame 5 has been acknowledged, that it implies frame 4 has been acknowledged as well. Also, at some point in time, the source may have sent frames, but not yet received the ACK. It is waiting for the ACK. Frames 6 and 7 in this example. And with sliding window, we're allowed to send up to some maximum window size of frames. And that's a parameter of the protocol. In this example, it's 7. We're always allowed to have a total of 7 frames outstanding. By outstanding, I mean I've sent them, but I haven't received the ACK. Or I could send them in the future, and I haven't received the ACK. In this example, at this point in time, we have sent 2 frames, frame number 6 and frame number 7. We haven't received the ACK yet. We're allowed to have a maximum of 7 outstanding. We've got 2 outstanding, so the window indicates that we're allowed to have another 5 to be transmitted, if we want. If we have data to transmit, I could transmit frame 0, frame 1, 2, 3 and 4. If I transmit frame 0, then of course that moves into this set of 6, 7 and 0 of frames that have been transmitted but not yet ACKed. So it's just the way that the sender keeps track of frames acknowledged, frames transmitted but not yet acknowledged, and frames that are allowed to be sent, such that the total of this is always the same. And in this example, it's always 7 frames. The receiver does a similar thing. The receiver receives frames, keeps track of the frames that it's received, and also acknowledged. So it's received the frames, passed them on to the higher layer, sent back an acknowledgement. We can think from the receiver's perspective they are complete. Frames that have been received but it hasn't yet sent an acknowledgement for, it may do so in the future. And frames that it may expect to receive in the future. Again, this is always 7 in this example, a total of 7 frames, because the receiver has a buffer space for 7 in this case, 7 frames. It cannot fit more than 7 frames in the buffer. It's currently got 2 frames in the buffer. It could handle another 5. This example showed what happened from the source and destination in terms of their windows or those variables that they keep track of. Initially we sent 3 frames. Why only 3? We're allowed to send 7, or maybe the source only has data to send 3. If we say every frame is 1000 bytes and we only have 3000 bytes to send, we can only send 3 frames, even though we're allowed to send another 4. After sending those 3, frames 0, 1 and 2 move into that set that are transmitted but not yet acknowledged. We're allowed to send another 4 at that point in time. We receive the 3 frames, send back an acknowledgement. In this case, the acknowledgement is called receive ready, just the special name of the acknowledgement here, but it's acknowledging that we've received some frames. It's saying the receiver is ready to receive frame 3, which implies that we've acknowledged frames 0, 1 and 2. Because they come in order, if we expect to receive 3 next, it must have mean 0, 1 and 2 have been received okay. After we send the acknowledgement, or receive ready, then the receiver is expecting to receive another 7 frames. It has space in the buffer for another 7 frames. And when A receives the receive ready message, that acknowledges frames 0, 1 and 2 that were sent, and so it's allowed to transmit another 7 frames. In this example, it transmits 4 frames. Again, it only has data to transmit 4. This is a different case where an acknowledgement or a receive ready was sent immediately after the first frame was received. And the end result, after receiving the receive ready, source A has frames 4, 5 and 6 transmitted but not yet act, 4, 5 and 6. And so there are 3 outstanding. It's allowed to have a total of 7, so there's another 4 that it could transmit in the future. You'll see always between the vertical bar and the end of the blue box is always 7 frames. 7, 7, 7, 7. And same at the receiver. That's the maximum window size in this example. So you can see the sliding window, the blue rectangle moves along. As we transmit frames, the rectangle closes on this side, so it goes from here to here. We can think of the window closing. As we receive acknowledgements, the window opens on the right-hand side. And as we transmit and receive, it will slide along. And similar at the receiver. There's another type of acknowledgement. In this case, we've got a receive ready. There's a special type of acknowledgement which is receiver not ready. It's given on the next, on 2 slides along. There's a frame called a receive not ready. RR was the receiver's ready to receive a frame. This is to say we acknowledge the previous frames, but we're not ready to receive any more. Our buffer is full, for example. If the buffer is full, we will not allow any more to be transmitted. So what we finished on last week was an example, what happens if we continue here. Let's give one more example. What happens if we continue? So destination B has received frames 3, 4, 5 and 6, transmitted receive ready 4, and after frame F6 is received, transmits receive ready 7. Then what happens if at this point we transmit receive ready 7? Then it means we're ready to receive frame 7, which implies the previous frames have been acknowledged. We've previously acknowledged frame 3 when we said we're ready to receive frame 4. Frames 4, 5 and 6 were received. Let's assume they were processed, removed from the buffer, and now the destination B is ready to receive more frames. So it sends back a response, an acknowledgement saying I'm ready to receive frame 7. And from the destination's perspective, the last frame act, acknowledged, that is this vertical bar would move along, would be frame 6. That is the last frame that we've received and acknowledged is frame 6, because we're expecting to receive frame 7. And we'd have a window size, or a current window size, of what? What do you think the current window size is? Destination B has, at this point in time, the blue rectangle is the window size. Currently it's 4 frames. We send receive ready, we acknowledge 3 frames. If the window was 4 and we've just acknowledged 3, what does that increase the window to?
4.
It's currently 4. When we acknowledge frames, it means we've got more space in the buffer. We expect to receive, or we will allow the sender to send more. So 7. Good. At this point in time, we had space for 4 more frames in the buffer. We send an acknowledgement, that is frames 4, 5 and 6 have been processed and removed from the buffer, therefore we can allow another 3 in the buffer. So you can think that this vertical line would move along to here, and the window would open out to cover from 7 through to 5. So the window size, we would be expecting to receive another 7 frames. We've got space in the buffer for 7 frames. And at the original source A, after we receive that acknowledgement, receive ready, is going to be a similar values. Last frame transmitted and acknowledged. What do we call it? Let's say last name act. The last frame that we received an acknowledgement for, we receive ready 7. That must acknowledge frame 6. And the current window the vertical bar moves along 3 positions because we've been acknowledged 3 frames. Therefore, we're allowed to transmit another 3 frames. The same window size. We'd have a window size of 7. 7 frames, that is. We're allowed to transmit now another 7 frames before we have to wait for an acknowledgement. And you can see over time, although they're not identical, the sender and receiver synchronise their view of what's allowed to be transmitted and received. So this is the mechanism for the sender and receiver to control what they are allowed to transmit and receive. Because the idea is that the receiver doesn't want the sender to overflow its buffer. The receiver will allow the sender to send multiple frames, but no more than a certain amount. And as the buffer space becomes available at the receiver will notify the sender and allow it to send more frames. And they keep track of how much is allowed to be sent using these values. Now, how does that improve our performance? Let's go through an example, and for those that haven't got it yet, take one of these. You take a handout and pass it along. This is the handout which is in fact the solution to this answer, and I've just given it in colour so it's a little bit easier to see the two different cases. What I want to do is show how sliding window can improve upon performance compared to stop and wait. We saw with stop and wait we transmit one frame, we have to wait before an ACK comes back. How can sliding window improve upon that? We've got a scenario here where we give some numbers. So the data frame contains 9,000 bits of data, 1,000 bits of header. Actually, we'll do it over here. Data frame is 10,000 bits in length, 1,000 header, 9,000 data. ACK is 1,000 bits. Transmission time with a data rate of 100 kilobits per second. What's the transmission time? With 100 kilobits per second, it's 0.1 megabit per second. Let's see if this is correct. And has everyone got a handout? I need one, so I know what I'm doing. They're all the same. The assignment will come later. So with a data rate of 100 kilobits per second, 10,000 bits divided by 100 kilobits per second is 100 milliseconds. And similar data, the ACK transmission time, 10 milliseconds. Propagation delay, 200 milliseconds. The other delays, processing and queuing, will assume 0. And in this example, we'll assume that we've got a lot of data to send. We've always got data to send. And that as soon as the receiver receives the data, it immediately processes and has space in the buffer for more. So it will immediately send an acknowledgement or receive ready. Just to see what's the best case performance that we can achieve. And the first case, we'll use a 2-bit sequence number. So in the header, which was 1,000 bits, and I only chose the number of these numbers so they give us numbers in the transmission time which are easy to calculate. The header has 2 bits, which is the sequence number. So the values that we can use are 0, 1, 2 and 3 with a 2-bit sequence number. So the handout you have in front of you will show what I'll quickly go through on the board of what's the timing associated with using sliding window. At the start, we're allowed to send the data frames from the source to the destination. I'll not draw the entire diagram here, but I'll show the frames being exchanged. And with a sequence number with 4 different values, the maximum window size, what do we call it? W or W max, the maximum size will set to 3. The maximum size should be, in general, the one less than 2 to the power of number of bits we have in the sequence number. Here we have a 2-bit sequence number. We have 4 values. The maximum window size should be 4 minus 1, 3. If we have a 3-bit sequence number, we'll have 8 values. The maximum window size should be 7. We'll see later why that's the case. But at this stage, the maximum number of frames we're allowed to have outstanding is 3. So, from the source, we can transmit 3 data frames at the start. I'll call it just data 1, D1. And each data frame takes 100 milliseconds to transmit. I won't show the units up here, but if we start at time 0, we'll finish transmitting at time 100, the first data frame. And from the source's perspective, we're allowed to send 3 data frames. So we send the first data frame and then immediately after transmit the second data frame. And then immediately after that transmit the third data frame. And each transmission is 100 milliseconds. So at time 300 we would have transmitted 3 data frames. Let's call it D0, D1 and D2. After transmitting the third data frame, since the maximum window size is 3, we would not be allowed to transmit any more. Let's bring up the example you have in front of you. So note that this example is the same as what we're going through here because we have a propagation of 200, data transmission time of 100, ACK of 10, 2-bit sequence number. So it's easier to show here. Transmit 3 frames. Why 3? Here we show the viewpoint of the source in terms of frames transmitted and acknowledged. Where, okay, we have a set of sequence numbers. Initially, the green 0, 1 and 2 are the frames that are allowed to be transmitted. Because at the start we haven't transmitted anything. Initially we're allowed to transmit 3 frames. So frames 0, 1 and 2 are allowed to be transmitted. We transmit frame 0. After transmitting frame 0 becomes one of the frames which have been transmitted but not yet acknowledged. We've sent it but we're waiting for the ACK. We're still allowed to transmit another 2 frames, 1 and 2. So we transmit frame 1. After transmitting frame 1, 0 and 1 have been transmitted. 2 is allowed to be transmitted. We transmit 2. 0, 1 and 2 are transmitted. We're still waiting for the ACK. We're not allowed to transmit anymore. This is where we must stop and cannot transmit anything. The maximum we're allowed to have outstanding is 3 in this case. So we transmit 0, 1 and 2. The timing associated at the end of 300 milliseconds, we've transmitted frame 2. In the meantime, those frames are propagating across the link. The propagation time is 200 milliseconds. So if we transmit frame 0 at 0, and we finish transmitting at time 100, or we transmit the last bit at time 100, it would take 200 to propagate and therefore the last bit would be received at time 300. The first bit at time 200, but the last bit of the first frame received at time 300, therefore the last, or the entire frame has been received at time 300. And in this case, we're assuming the processing time is very small, so we'll just say it's 0. The frame is received, processed, everything's okay, send the data to the higher layer, and immediately we'll send back an acknowledgement, an ACK frame or receive ready. And this is the acknowledgement transmitted here. It takes 10 milliseconds to transmit, so that propagates back, and the acknowledgement will be received at time 510 because we have a 200 millisecond propagation delay. In the meantime, as we receive the first frame, or frame 0, we start transmitting the ACK, we start receiving frame 1, and then we receive frame 2. And in the same manner, we transmit the acknowledgement for those frames. So in this example, we're sending one acknowledgement for every data frame received. It doesn't have to be that, but in this example, we're using that. So an ACK for frame 0, an ACK for frame 1, and an ACK for frame 2. Let's see what happens. I haven't drawn the window at the receiver, but you could calculate that if you like. We just focus on the sender. So at this time, after transmitting frame 2, the sender was waiting for the acknowledgement for 3 frames. Not allowed to transmit anymore. It's waiting, it's waiting, it's waiting. It's not sending anything. And you know that this is going to be lead to some inefficiencies, because the more time we spend sending nothing, the less efficient we are. We're waiting. We receive the first ACK. The ACK has come back at time 510. After receiving the ACK, I don't show what it is, but it would be receive ready with what value? ACK with some number, or receive ready with some number. What would the value be in that case? In our slides, we call it receive ready, and we had a number. What would be the number included in this receive ready? What do you think the number is going to be? What value are we ready to receive? What value do you think we're ready to receive at the B? This is the acknowledgement after receiving the first frame, frame 0. So we send back an acknowledgement with the value anyone? What value is going to be included in our acknowledgement? What do you think? We've sent, now remember, let's make this clear, this D0 is this data frame 0. The 0 is the sequence number in this frame. Data frame 0, 1 and 2. Receiver receives data frame 0. It sends back an acknowledgement. And I think in all the protocols we will see, if there's a number associated with the acknowledgement, it's saying, the acknowledgement means thank you, I've received something. The next number I expect will be 1. I've received data frame with sequence number 0. I'll send back a receive ready. I'm ready to receive frame 1. So that's the first acknowledgement coming back. when the source receives this, because it knows that the receiver is ready to receive frame 1, that implies that frame 0 was received. So we acknowledge with the next number, not with a number that just received. Therefore, from the source's perspective, frame 0 moves into the set of frames that have been transmitted and acknowledged. 1 and 2 are still outstanding. We've transmitted 1 and 2, but we're still waiting for their ACKs. They haven't arrived just yet. And we're allowed to transmit one frame more, because we're always allowed to have a maximum of 3 outstanding. We've got 2 transmitted, we're allowed to transmit one more, which would be frame 3. So we transmit frame 3. And after we transmit frame 3, 1, 2 and 3 will be outstanding. 1, 2 and frame 3. Then we'll receive, or in fact at the same time, at time 610, we'll receive the second acknowledgement. This was the acknowledgement for the first frame. Sometime later, we received the acknowledgement for the second frame. The second frame was, data frame was sequence number 1. Therefore it says receive ready 2. I've received frame 1, I'm ready to receive 2. And that's in here, we receive this acknowledgement, which indicates that frame 1 has been acknowledged. 2 and 3 are outstanding, 2 and 3. I'm allowed to transmit one more, frame 0. So I transmit frame 0. And we get to this state. 0 and 1 have been acknowledged. So 0 and 1 are complete. 2, 3 and 0 are outstanding. Transmitted, still waiting for the ACK. And that's shown here. And then we'll receive the next acknowledgement, which is the acknowledgement for frame 2. You see frame 2 transmitted, ACK comes back, arrives back, means frame 2 is now complete. I'm allowed to transmit one more frame, frame 1. I transmit frame 1, so now 0, 1 and 2 are complete. 3, 0 and 1, these 3 are outstanding. That is, we're waiting for an acknowledgement. And we cannot have more than 3 outstanding at a time, so we cannot transmit any more. If we keep going down, we'll see the pattern starts to occur. If we went forever, frame 3 was transmitted starting at time 510. The times here are just calculated by the transmission time, propagation time, transmission of the ACK. In fact, so the transmission of a data frame is 100, propagation brings us to 300, plus the ACK, 310, plus another 200 for the ACK to propagate, 510. You'll see from here to here is 510. For the next frame, it's 510, 510. The answers are here. After transmitting frame 1, we have 3 outstanding. We cannot transmit any more. We have to wait for an ACK. We're waiting for the next ACK. Eventually that will come, acknowledging frame 3, allowing us to send another frame, and when we send that, then frames 0, 1 and 2 will be outstanding. The next ACK will come, acknowledging frame 0, allow us to transmit frame 3, and 1, 2 and 3 are outstanding. The next ACK, and we'll keep doing that for as long as we've got data to transmit. See the pattern that's shown in this example. transmit 3 frames. Wait for the first acknowledgement to come back. Transmit another 3 frames. Wait for the acknowledgement for the first of those transmitted to come back. That is, when the acknowledgement for frame 0 comes back, we're allowed to transmit more. When the acknowledgement for frame 3 comes back, we're allowed to transmit more. So if we keep following this, we transmit 3 frames. When the acknowledgement for the first comes back, then we'll transmit another, and then the acknowledgement for the next, and so on. And we'll be in this pattern of transmitting 3 frames, waiting, another 3, wait, another 3, and wait. So on average, or if I zoom out on that pattern, it would look something like this. I haven't drawn in detail, but we have 3 frames transmitted. When the acknowledgement for the first frame comes back, we'll be allowed to transmit more. And when the acknowledgement for the first in that set comes back, we can transmit more. And we'll keep doing that. So frame 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, and so on. That's just a zoomed out of this diagram. In general, what we see is this pattern is, in this period of time, we transmit 3 frames. And the receiver receives 3 frames because we've got nothing being lost. And then in the same period of time, let's say T, transmit 3 frames in this time, and then transmit 3, wait, the same time T, another 3 frames transmitted, and then another 3 frames, and then another 3, and so on. So we're transmitting 3 frames every period T, and then another 3, and another 3, and so on. Similar, we're receiving 3 frames every period T. What is this duration of T? Well, we've got the numbers here. We start at time 0, leads us to 510. So the first 510 milliseconds, the second 510 milliseconds, the third 510 milliseconds. Every 510 milliseconds, we're transmitting 3 frames, and therefore we're receiving 3 frames. And you can keep going in this case to see the exact timing for the other cases, for the remaining frames. That gives us our throughput, or efficiency. 3 data frames. Each data frame, if we go to the top or back to the question, contain 10,000 bits, 9,000 bits of real data. It was 9,000 bits of data plus 1,000 bits of header. So we have 9,000 bits of real data, but we have 3 lots of that, 3 data frames, every 510 milliseconds. And that gives you, and it's on the sheet in front of you, in fact, the question gave us a data rate of 100 kilobits per second. It's approximately, it's not on the sheet in front of you, (52.94 kilobits per second). It's not in this handout. On the original question, the In the lecture notes, we had a data rate of 100 kilobits per second. Gives us a throughput of 52.94 kilobits per second, or an efficiency of 52%. 52.94%. And that's the answer in the handout that you have in front of you. So that was with the case of a maximum sequence number or a maximum window size of 3 frames. Transmit 3, then we had to wait. Transmit another 3, and so on. The second diagram is the same scenario except a different maximum window size. Everything's the same here except we have a 3-bit sequence number. With a 3-bit sequence number we can go from 0 up to 7. And we have a maximum window size of 7, which means we can have a total of 7 frames outstanding before we have to wait for an ACK. So if we follow through the same process, this diagram shows what we'll result with. Initially we're allowed to transmit 7 frames, 0 through to 6. So we start transmitting frame 0, immediately after that frame 1, frame 2, 3, 4, 5, 6, and then we will wait for an acknowledgement. But with this scenario, if we transmit frame 0, the ACK will eventually come back at time 510. The ACK for frame 0. Every time we receive an ACK, we can transmit 1 more frame. So we can transmit 7 frames. After transmitting frame 0, another 6, another 5, another 4, another 3. We can transmit another 2 frames. And then an ACK comes back. Actually, another 1 frame here. The ACK comes back for the first frame that was transmitted. So frame 0 is now acknowledged, allowing us to transmit 1 more frame. We can transmit another 2 frames now, 6 and 7. We transmit 6, and as we're transmitting 6, the ACK for the second frame comes back, allowing us to transmit 1 more, which is frame 0. And we keep going, we transmit frame 6, an ACK for the third frame comes back, allowing us to transmit frames 0 and 1. Because we can only transmit 1 frame at a time, the ACKs are coming back before we've completed transmitting our window. We were originally allowed to send 7, but before we completed sending those 7, which was here, we started to receive acknowledgements back. And they allowed us to send more. And that will keep going for as long as we have data to send. We just continuously transmit frames because we keep receiving acknowledgements for our previous frames, which allows us to send more. You'll see that the allowed set of frames is always greater than 0. We're always allowed to send at least 1 frame, which means we never stop transmitting. If we're transmitting frames all of the time, then we're receiving frames all of the time. And this is the best case efficiency that we can achieve because we've got no time waiting. There's no time between sending a frame and then waiting for an ACK to come back with this scenario. So the efficiency, and it's calculated down the bottom, the only overhead in this case is our header. Our data frame had 10,000 bits. 9,000 bits were real data, 1,000 bits header. There's no time spent not sending, and therefore we have an efficiency of 90%. Always transmitting. 90% of the time we're transmitting real data. 10% of the time we're transmitting header. Therefore we get an efficiency of 90% or a throughput of 90 kilobits per second if our data rate is 100 kilobits per second. So in exactly the same scenario using sliding window, by increasing the maximum window size, we can improve our efficiency. What if you set the window size to be 1, what happens? Efficiency goes up or down? The maximum window size is 1. What's going to happen? We've gone through 2 examples. First one, maximum window size is 3. The second one, maximum is 7. What if we set it to 1? Will our efficiency go up or down? Down. In fact, if we set it to 1, it's the same as stop and wait. Stop and wait, transmit 1 frame, then we'd have to wait for an act to come back. Transmit another frame, wait for an act to come back. So stop and wait is in fact just a special case of sliding window where the maximum window size is 1. Sliding window generalises where we can have n frames transmitted. Stop and wait is just 1 frame at a time. So in the same scenario, if we use stop and wait, our efficiency would be much less than what we had over there of 53%. I don't know what it will be, but quite small. So in general, with increasing the maximum window size in sliding window, we improve our efficiency under the same conditions. We spend less time waiting. Any questions on sliding window before we move on to our next topic? So this has shown how it improves the performance compared to stop and wait, and in different cases of sliding window. Any questions?
No.
Sure?
Can I have the paper?
Yes, you can. Anyone hasn't got the handout?
This one, three number of maximum of windows. But this one got 7. But this one can the data will the app will switch back after the window size is the maximum window size is reached. But this one it doesn't reach the maximum window size. It can send the app back.
Okay, let me explain. So there's a question about if we compare the case of window of 3 and window of 7, when does the act come back? Going back to the first case with a maximum window of 3. The act comes back whenever the destination B has received data. It's not to do with the window size. Transmit data, receive the data, immediately send the ACK in both cases. So the ACK comes back at time 510. The time 510 is simply if we transmit at time 0, transmission time, propagation, transmit the ACK, propagate, comes back at 510. And in the second case, the first ACK comes back at the exact same time. So the time and when the ACK comes back is not related to how big the window is. It's simply related to the propagation and transmission delay. The difference between the two cases is because of the values of the propagation and transmission delay of 200 for propagation, 100 for data, because we have a large propagation delay, it takes a long time for the first data frame to be acknowledged. The time from here to here is large, larger than transmitting 3 frames. But from here to here, it's smaller than transmitting 7 frames, which we see in the next example. The time to get one acknowledgement back is also 510. Transmit the first frame, ACK comes back. The first ACK comes back before we've finished transmitting our first 7 frames. Every time we get an ACK back, transmit another one. So receive the acknowledgement back, we're allowed to transmit another frame. So it's related to, or the trade-off, or the difference in performance is related to the propagation delay, the data transmission time, and the maximum window size. If we set the maximum window size to 1, we said that we'd get a lower efficiency. What if we set our sequence number to be a 4-bit sequence number? What's going to happen? We have a quiz tomorrow, is that right? With a 4-bit sequence number, what's going to happen? Efficiency go up or down? Some people have said up, some are same, some down. If with a 4-bit sequence number, then we can have 0 up to 15. Okay, so we can transmit a maximum of 15 frames. But we'll get the same scenario as here. We'll transmit frames 0, 1, 2, 3, 4. In fact, we won't finish at 7, we'll go 8, 9, 10 and so on. We'll receive the first ACK back, allowing us to send one more. With a 4-bit sequence number, or allowed to transmit 15 frames, we'll keep transmitting frames. That'll be no better than in this case. In this case, we've got the best performance we can achieve. We're always transmitting, no time waiting. We cannot improve upon that unless we reduce the size of the header. So in this scenario, increasing the window above 7 to 15 to 31 to larger does not improve the performance. So it's related to the propagation and the data transmission time as to what's the most appropriate window size. Let's go back to our slides and see what we've missed. So, sliding window we've gone through where we allow to send a window size of frames before waiting for the ACK. Can improve upon efficiency compared to stop and wait. We've already mentioned that there's a special receive not ready type frame. It's used if the receiver has received data but has no space in the buffer. In the previous example we said that there was always space in the buffer, but of course in real life that may not be true. In some protocols, well, in most cases, we want to transmit data in both directions. All our examples up until now, we've been sending data from A to B, not back. But in most cases, we want to send data from A to B, and B would want to send data to A. So we can use the same protocol, but in both directions. To make things a little bit more efficient, when we send an acknowledgement from B to A, acknowledging data it's received, we can include that acknowledgement with some data being sent from B to A. And that concept is called piggybacking. We piggyback an acknowledgement on a data frame. Let's try and illustrate what we mean by that. Consider we want to send data in both directions. And piggybacking applies to sliding window, stop and wait, and many protocols. We'll just look at the concept. We transmit data, and then we'll transmit an acknowledgement in response. And if we wanted to transmit data from B to A, we could do that separately. and an ACK would come back. So we can apply our protocol in one direction and have a separate instance of that in the opposite direction. Piggybacking combines these together into one packet, one message. In this example, we send one data frame to B, B sends an ACK frame back, and then B sends a data frame. But that can be a waste. Piggybacking allows us to combine these into one, where, we'll draw it here, transmit the data frame. Instead of sending two different frames, send a data frame, and included with that data frame an acknowledgement. Just combine the two frames together. And the reason we can do that in most cases is because an acknowledgement is normally just the header, or specifically some fields in a header. So what we do is, in our example, we had a frame which had data and a header, and an acknowledgement frame which was just the header. The acknowledgement frame contains, for example, the number and the type of frame, receive ready 3. The header contains a sequence number. For example, sequence number 2 of the data. All we do is include fields from the acknowledgement header in the data header. So we send one frame, but it has two meanings. The meaning of that frame is, here's some data from B to A, as well as, here's an acknowledgement from the data I received from A. That's the concept of piggybacking. We'll see that used in TCP when we look at transport protocols and other protocols. It means we cut down on the number of frames transmitted, save this transmission time. And there are some other optimizations of sliding window, but I think that's the main thing that we need to focus on. Okay, we have 10 minutes remaining. Any questions? We'll say a little bit about the assignment for those that came late. Any questions? Everything's easy? You'll get full marks in the quiz? Okay? Not okay. What's not okay? Let's make sure this is okay first. Yep. What do you mean finish? Okay. Coming back to our sliding window example, there's a question. Find it. This is just one example, and in this example, assume we've got an infinite amount of data to send. We want to send data forever. So, in fact, it wouldn't finish here. If we keep drawing this box, we'd keep going forever. 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. And all this is showing is that frames which have been transmitted to the left and acknowledged, the frames which are outstanding, we're waiting for the ACK, and in some cases we're allowed to transmit. So we may not finish if we've got an infinite amount of data. If we've got a fixed amount of data, if every frame was 10,000 bits and we only had to send 20 frames, then as soon as we receive the ACK for the last frame, we're finished. Note that the sum of the red blocks and the green blocks is always 3 in this case. That was the maximum window size. And in the next example was always 7. The maximum window size in the second example is 7. Does that answer? Yep.
I don't understand why piggybacking is more efficient than this.
Okay. The concept of piggybacking is general, not just for this protocol, can be used in many different protocols. Normally we want to send data in both directions. All the examples, we're sending data just in one direction. Send data, send back an ACK frame. But it turns out what an ACK frame is simply the main things are the source and destination address, where it's coming from, who it's going to, and, for example, the sequence number that we're acknowledging. So with piggybacking, what we can do is, in the data frame, the header, in the data frame header, we include the sequence name, sequence number of the data, data 2, and we include one additional field, which would be the acknowledgement number, receive ready equals 3. So we add one more field to this header. We don't need to transmit, if there's a source address and a destination address. And same here, we have a source and destination address. Without piggybacking, we transmit an ACK frame, which includes the source and destination and the acknowledgement number, and maybe some other information. And then we transmit the data frame, and the header of the data frame includes the source and destination, which are of course the same, and the sequence number of the data. With piggybacking, we combine all of that information into the data frame. Data frame header contains the source, destination, sequence number, ACK number. So we don't have to transmit the entire header again. So essentially we're saving this much transmission. So there's a small amount of transmission time we save. We reduce the transmission time. That can be applied to many protocols. Any other questions? If he doesn't know, are you going to know?
What's the benefit of combining the ACK frame with the data frame?
The benefit is the reduced transmission time. Let's give it some numbers and make it a little bit clearer on a diagram. In our example, we said we had a data frame which had 9,000 bits of data and 1,000 of header. The header contains many different pieces of information, including the source address, an address of the source computer, an address of the destination computer. It may contain something like the version of the protocol we're using, other information used for that protocol. In our case, the data frame contains a sequence number, I say SN. Let's say the source address is 32 bits. That's an IP address. Destination is 32 bits. Sequence number in our case was, what do we have? In the first case was 2 bits. And maybe there's other fields. total of 1,000 bits. 1,000 is not a very good example here, but just continuing on from our case. And the ACK is just a header. 1,000 bits. Contains a source, a destination, the acknowledgement number. We denoted it as the receive ready number. And it's also a 2-bit number in our example. And maybe other fields as well. If we transmit an ACK frame and then a data frame, then we need to transmit the 1,000 bits. Actually, first we transmit the ACK frame of 1,000 bits, and then we transmit 1,000 bits of our data frame, a total of 2,000. That's without piggybacking. We need to transmit the 2 frames separately, one after the other. With piggybacking, what we do is inside the header for the data frame, we include another field which includes at least the acknowledgement number, the receive ready number. So let's say we make it larger. Instead of 1,000 bits, we increase it to 1,002 bits. 1,002 because it includes all the existing fields plus the 2 bits for the receive ready. So with piggybacking, we transmit the data frame, and inside the header we include the information contained in the ACK, which includes the receive ready field. So with piggybacking, we just transmit 1 frame, which is a header of 1,002 bits. Without piggybacking, we had to transmit 2 headers, data frame header, ACK header, 2,000 bits. With piggybacking, we just transmit 1, although it's slightly larger, not by much. So in effect, we save on the transmission of headers. And that can be quite significant if we have a small amount of data. So it's a small saving in the transmission of the amount of overhead that we send. Because most of the fields in the ACK frame are the same as in the data frame, especially if they're going in the same direction. The source and the destination in the data frame sent from B to A, and in the ACK frame sent from B to A are the same. Source B, destination A. So we don't have to duplicate all those fields. Does that answer the question about the savings? So it's only small in some cases, but it can be significant if you're sending many frames. Let's see if we've finished this topic. That brings us to the end of sliding window, or generally end of flow control. The next topic, and the last one on data link control protocols, very similar but error control. We won't go through it now. We will use stop and wait and sliding window, same concepts, but now in the next lecture we'll consider what happens if we lose a frame. I transmit frames from A to B, one of them doesn't get there. How can we detect that error and retransmit, correct the error? So we'll look at the error control mechanisms available for retransmissions, and we'll see that they're based upon stop and wait flow control, and the other 2 mechanisms are very close to the sliding window mechanisms, so very similar to what we just covered. We will cover that tomorrow.